All right, so we are back for the second part of 314, Defining Rigid Transformations, where we're just taking all of the different types of transformations that we've discussed so far and pulling what we know about all of them sort of together into one place. Evan has graphed the point 5,7, and he wants to reflect it over the line y equals negative 2/5 x plus 6. He predicts that the reflected point will have coordinates 2, 2. Without graphing, can you confirm his answer or show that he cannot be correct? Explain. So what we want to do is say, instead of grabbing a ruler and actually connecting those dots and then grabbing a protractor and measuring the angle, is there a way to tell algebraically if that segment would be perpendicular? And so we want to go back to the parallel and perpendicular section that we just did and say, in order for two things to be perpendicular, their slopes have to be opposite reciprocals. So we want to find the slope of the line that would connect 5,7 to 2, 2 and see if it is the opposite reciprocal of the line currently on the page, which has a slope of negative 2/5. So if we wanted to do that, 5,7 and 2, 2, we would need to find the slope, and we would do 7 take away 2 over 5 take away 2. That's the y2 minus y1 over x2 minus x1. And we would get that it has a slope of 5/3. So the line has a slope of negative 2/5, but the 2 points would have a slope of positive 5/3. In order to be an opposite reciprocal, it would need to be positive 5/2. So very close, but the slopes are not opposite reciprocals, so they're not perpendicular. And we're talking about the slopes of the line of reflection, which was negative 2/5, and the 2 points, which had a slope of 5/3, are not opposite reciprocals. All right. Translations. Everybody likes the translations more. And if anybody is curious, a current functional reason that this is really important stuff, anything you do with graphic design, video game design, is going to rely on things like rotations. If you have a character that's turning, translations, if you have a cloud that's shifting in the sky, reflections, clearly a mirror, but also if you had like a mirror image in a lake, things like that. Those are all based on this lesson. All right, so translation. The formal name for a slide is a translation. So what exactly is it? Translation and transformation are two different words. Translation is the slide. Transformation is a big change, and you can think of transformers having many different types of changes. Triangle A prime, B prime, C prime at the right is the image of a translation of triangle ABC. Describe the translation. So in order to describe it, we'd want to know how many units did it move to the right and how many units down. So everything's moving horizontally and vertically. So this is going to be 1, 2, 3, 4, 5, 6, 7 to the right. So that's a +7. And then 3 units down, which would be a -3. So 7 units right, 3 units down. Sorry about the smushy right there. If we wanted to describe that with the right notation, we would say that the points x, y translated, and x went to the right 7, so x plus 7, and y went down 3, so y minus 3. We can also check the other points to make sure that it's a transformation, that it's rigid, that the shape stayed the same size and the same shape. So you could also check, for example, from A to A prime, and you could say to get from A to A prime, I had to go right 7 and down 3. And then you could, if you wanted to be very thorough, you could also go 1, 2, 3, 4, 5, 6, 7 down 3. And all 3 of them are the same, which also confirms that it's a translation, that the shape stayed the same size, same area, same angles, and all of that. On graph paper, plot triangle EFG with coordinates 4, 2, 1, 7, and 2, 0. What are the coordinates of E prime, F prime, G prime if it is translated the same way as triangle ABC? So you'll notice that we put over here x plus 7, y minus 3. Well, the great thing about having this type of notation is that you can literally just add 7 and subtract 3 to each coordinate. So I could, to get E prime, I could do 4 plus 7 is 11, and then 2 take away 3 is -1, and that would give me the new coordinates for the translated shape algebraically. It would actually allow us to skip the graph altogether. So 1, 7, if I add 7, I would get 8. And then the second coordinate 7, if I subtract 3, I get 4. And for G, it's 2, 0. If I add 7, I get 9. And the 0, if I take away 3, I get -3. So the graphing of this, I'm just going to slide a different page under here so that you can see it. The graphing of this shows two triangles. They stayed the same size and the same shape. They are congruent. So it's definitely a rigid transformation. And you can also see that I connected each one of the points, F to F prime, E to E prime, and G to G prime, and they all stayed the same length. Those red segments are the same length, which also tells us they would have the same slope triangle. For the translated part in part B, draw line segments connecting. So we did that. What does it tell us? It tells us that the red segments are congruent. You will also notice that they're parallel. So you could also label them with that little arrowhead for being parallel. What does it tell you about a translation move each point? What does it tell you about how a translation moves each point? It moves each point the same distance, and it moves it in the same direction. You could also use tracing paper or wax paper to double check both of those translations as well. All right, so we've got the last page, connections to algebra. Read the math notes box in this lesson. So there's a section of math notes that we have available, and you can check those as well. Note that the formal definitions of transformations involve functions. Plot triangle ABC on the grid below left with points 3, 3, 1, 1, and 6, 1. Apply the function xy if it becomes -x, -y to find the coordinates of the image. For example, using the given function, the original point, 8, -3, would become -8, 3. So what we're going to do is we're going to graph 3, 3, 1, 2, 3, which is A. We're also going to graph 1, 1, which is B, and we're going to graph 6, 1, which is C. So that's our original. And then we want to change that to -x, -y. So if A was 3, 3, A prime is going to be both negatives, but they stay in the same order. So -3, -3. B prime would be -1, -1. And C prime would be -6, -1. So then I can go down and graph the first -1, -1, -3, -3, and -6, -1. That would be our what? What type of transformation is that? So let's say A prime, C prime, B prime. It did change its orientation. Notice C was on the right, now C is on the left, but it's definitely not a reflection. And A was at the top, but now A is at the bottom. That makes it a rotation. And because it went from quadrant 1 all the way over to the opposite quadrant 3, it makes it 180-degree rotation. Notice I don't have to say clockwise or counterclockwise because it's 180. Use the function xy becomes x minus 6, y minus 6 to transform the triangle ABC again. Name the coordinates of the image A double prime, B double prime, C double prime. Now notice it had us go back to the original triangle. It said to transform triangle ABC. So we're not transforming this image. We're transforming the original one. And this particular transformation is a slide. It's a translation. And I can tell that because it's subtraction and addition. So by going x -6, y -3, that's going to be a translation left 6 units and down 3 units. And notice I always say units. I'm never like down 3. Units, because I'm not counting it in centimeters, I'm not counting it in inches, I'm not counting it in miles. You have to say units because it's whatever this square is worth. So if I'm going to translate 6 units left, 3 units down, 1, 2, 3, 4, 5, 6, 1, 2, 3, that puts my A double prime here. 1, 2, 3, 4, 5, 6, 1, 2, 3. That puts my B double prime here. And then 1, 2, 3, 4, 5, 6 puts me right on the y-axis. And C double prime here. And that was a translation or a shift. It kept its orientation. It's still facing the same direction, still upright. On the new set of axes, plot and connect the points to form quadrilateral WXYZ if the vertices are 3, 7, 3, 1, 2, 3, 4, 5, 6, 7. And that one's going to be W. And 3, 4, 1, 2, 3, 1, 2, 3, 4. Nope, sorry, that one's X now. 9, 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 1. And that's Y. And Z is 5, 6. All right, so I've got kind of a kite, almost a kite, but not. So it's going to be just a quadrilateral. Transformed by the function X becomes negative X and Y stays Y. So you'll notice this thing isn't going to change in height. If Y stays Y, it's not going to move up or down, but X becomes negative X. So it's actually going to change the shift from left to right. So if this coordinate X was 3, 4, now it's going to be negative 3, but still 4. That's X prime. And then Y was 9, 1. Well, now it's going to be negative 9, 1. And that's Y prime. Let's see. And then W was 3, 7. And now it's going to be negative 3, 7. Let's see. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7. That's going to be W prime. And then Z prime. Z was 5, 6. So now it's going to be negative 5. 1, 2, 3, 4, 5, 6. And you will notice that this was a reflection. So Y prime ended up back at negative 9, 1. And it is a reflection over the Y-axis. And it seems a little counterintuitive. Notice that the X is what changed. So think about if X is changing, the side-to-side change that's happening, it's changing from being on the right to being on the left, which means in order to do that, it's changing from the right side of the Y-axis to the left side of the Y-axis. Another way to write that would be that it is a reflection, which was lowercase r, of the Y-axis, and that's XY becomes negative XY. And that was from your little cheat sheet, those rectangles that were on the notes. Facts about isosceles triangles. So this is just a wrap up at the end here. How can transformations such as reflections help us learn more about familiar polygons? Consider reflecting a line segment across a line that passes through one of its endpoints. So one of the endpoints of the segment B is actually on the line of reflection, and so it will stay on the line of reflection. Copy the diagram at the right. You don't need to copy it because it's on the paper. And draw A prime B where we reflect it. So in order to reflect it, you would want to grab a ruler, and we'd want to make sure that we stayed at a 90-degree angle. And we would want to measure how far. It's about 1 centimeter to the left. Maintaining a 90-degree angle with the line of reflection, we'd want to go 1 centimeter to the right. And that would give us A prime. And then we could connect B down to A prime. Not only would this point be B, it would also be the B prime point because it stays on the line of reflection. And this is how we would get an isosceles triangle because BA is the same length as BA prime. So let's see, AB is congruent to AB, and that A is the prime, A prime B. Also, angles. Would you have congruent angles? Sure you would. You'd have that angle A would be congruent to angle A prime. They'd be the same size. So we can say angle A is congruent to angle A prime. Anything else special about this polygon? It happens that because we reflected it and we made sure that we had that 90-degree angle, we could say that the line of reflection is perpendicular to AA prime, meaning it made a 90-degree angle. And we did that on purpose because it needed to have a 90-degree angle. So the line of reflection is perpendicular to AA prime, that segment at the bottom. And it does something else kind of neat. Because we went 1 centimeter to the left and 1 centimeter to the right, it also bisects that segment. And anyone who needs to remember, bisect means to cut in half. So the left side is equal to the right side. It bisects, bi meaning 2, cuts it into 2 equal parts. So I understand this was a longer video than normal, and we don't often have these. but it does take a while to do the graphs. So I will see you in class, and hopefully this was just sort of a wrap up and a connection back to the previous 3 sections. See you soon.